If we take the example in an industrial unit where we want to build a model which is able to predict whether there is a defect on a specific equipment or not. Clearly, most of the time, this equipment is going to be non-defective. So it's going to be very easy for us to get a data for when the device is non-defective as compared to when it's defective, as the equipment gets bad very rarely. Now let's take another example where we have this data points with inputs an image and then outputs 4 possible classes to which this image may belong. Let's suppose that for class 1, that is, we have 300 images which belong to class 1, and then 10 images belonging to class 2, 3 images belonging to 125 images belonging to class 3, 125 belonging to class 4. Clearly from this, our data is imbalanced since we have class 1 having way more data points compared to class 2, and also almost twice or more than 2 times more data as compared to images which belong to class 3. And the way this problem can be solved is by using or working on the loss function. Supposing we have this model, obviously we will be using a categorical cross entropy loss, which takes in the y true and then the y pred. What we will do is we shall, for every output batch, break it up into several parts. The first part will constitute outputs for which the true value belongs to class 1. The second part, outputs for which the true value belongs to class 2, this class 3, and this class 4. So we break up the calculation of our loss in 4 parts. Now, we shall now multiply each part with a corresponding factor. And the way we shall multiply each part is such that classes like the class 2, which have very few data points, will have a higher factor. Now, the reason why we're doing this is so that these classes should have more effect on the loss calculation and hence on the optimization of the weights. Then we also make sure that this factor for the classes with much more data points is smaller compared to this other classes with fewer data points. If we apply that strategy here, lambda 1 could be 560 divided by 300. Now, if we are doing this, note that we could calculate the total data set size. That's 500 plus 300 plus 10, 310 plus 250, that's 560. So we have the total data set size divided by the number of data points belonging to class 1, which is 300. Here's 10, here's 125, there's 125. So the values of lambda range from about 1.7 to 56. You could also normalize these values by dividing all these values by the highest value of lambda, which is 56 in this case. So we're going to have 1.7 divided by 56. 56 divided by 56 will give 1. Then this divided by 56, that should give something like 10 on 125. And here 10 on 125. So the values will range between 0 and 1. Then once this is done, we could go ahead and train our model. Note that without taking care of data imbalance, we may face a problem where our model appears to be performing very well, but this performance will be more reflective of the classes with the highest data points. And when this model will be given data whose output is meant to be of, say, class 2 with lower data points, the model will perform very poorly. And so that's why we need to apply data imbalance, so that during training already we account for the fact that some data points contain more data than others. Now, to conclude, we could generalize the formula for getting this factor by saying we can look for the total number of data points divided by the number of data points in the class specified. So like for this, the total number of data points in class 3 is 125. Total number of data points 560. So we have 560 divided by 125.